Welcome to screencast number 1 for Unit 8, Lesson 3. I'm on page 452 and we're going to start talking about weather. But before we really get into the details of weather, we need to understand the underlying causes of, those things that are ultimately going to produce our weather. So I'm just under the first paragraph where it says, what is weather, the blue heading. And look down there where it says weather is the short-term state of the atmosphere at a given time or place. Weather includes many factors: temperature, humidity, precipitation, air pressure, wind speed, wind direction, and visibility are all part of weather. And we will get into what those all are in more detail in Lesson 4. Lesson 3, we're still trying to understand the underlying causes of what is going to produce our weather. So, let's go down to the next blue heading where it says, how is solar energy related to weather? The sun does not warm all of the Earth's surface evenly. Areas near the equator receive more incoming radiation from the sun. Okay. Go ahead and highlight this sentence also. In the tropics, over time, incoming solar radiation is greater than the radiation that goes back into space. In contrast, the middle latitudes and the poles receive less incoming radiation than outgoing radiation. Basically, what they're saying is towards the equator, which the tropics is basically your region around the equator, you're getting a lot of incoming solar radiation. You're getting a surplus. Surplus means extra. So you're taking in, or the Earth is taking in more heat from the sun than it is radiating back out into space. So we're gobbling up heat, but we're not getting rid of enough. So that's towards the equator, the tropics. The opposite is happening towards the poles. You are losing more heat energy to space towards the poles than you're getting from the sun. And so you get, a surplus extra heat energy absorbed at the equator, and you get a deficit at the poles. Okay, so here's a couple of little tidbits I want you to write down up here. A couple little terms I just used, and I want you to make sure that you understand the words that I just said. So hang on just a second. I'm going to write a couple of them down, and you're going to prove that you're listening because you're going to give me a one-word definition for those words. Okay, so remember, if I say something about the tropics, I'm talking about areas near the equator. So that's what you need to write in for tropics. Areas near the equator. That's not y'all's bell. That's just the 7:30 bell in the morning. Okay, so tropics, areas near the equator. Surplus is just a word that means extra. So if you have a surplus of something, you have more than you need. If you have a deficit, then that means you don't have enough. So deficit, a one-word definition would be shortage. Okay, so areas near the equator, extra or more than you need. Deficit, not enough or shortage. Okay, so when I use those words, I want you to understand what they mean. All right, you have seen a picture similar to this when we covered seasons in Unit 5. And y'all know that areas near the equator, the sun's rays are hitting pretty directly. They are cutting through the atmosphere directly, and the sun's rays are very concentrated. So we're getting a lot of heat energy absorbed in these areas. Okay? In contrast, areas closer to the poles, the sun's rays are coming in and hitting at more of an angle. Also, they're having to travel through more of the atmosphere. And so we have less heat energy being absorbed towards the poles. And one of the things that's going to drive weather patterns, as you'll find out, is the fact that we're getting a surplus of heat energy at the equator or near the equator, and we have a heat energy deficit at the poles. So one of the big things that weather does is it tries to even out our heat energy. So there are things that are going to take the excess heat energy from the equator and try to distribute it up towards the poles where there's a deficit. Okay? Okay, so down here, continuing under the topic that says, how is solar energy related to weather? Energy as heat is transferred from the warm tropics toward the colder poles. It's transferred by air that moves in the atmosphere and by water that flows in the oceans. This is really important. This is all about what was happening in lessons 1 and 2, which we kind of condensed down. But it's, we need to understand winds and we need to understand ocean currents, because those are the things that are going to redistribute the heat energy. Those are the things, air currents and ocean currents. Those are the things that are going to carry that excess heat from the equator to the poles. Okay, so that's really important. All right, join me on the next page, 453. All right, on page 453, it says, what are convection currents? Well, energy as heat is transferred mainly by convection. Convection is one way of moving heat energy around. Convection is the movement of matter due to differences in density caused by differences in temperature. Okay, so that's all fancy and everything, but what that really means is things that are warm, when things are warmed up, they expand. If you take air and warm it, it expands. It likes to occupy a bigger space, which makes it less dense. Same thing with water. Warmer water is less dense than cooler water. So what winds up happening is when air or water is warmed, it becomes less dense and it wants to rise. And cooler air or cooler water sinks because it's more dense. And so when you get warm air rising and cool air sinking, you wind up producing a convection current. All right, I'm going to show you an example of some convection currents in just a second. But before I do, just to prove that you are listening, find where it says denser matter sinks and highlight that. Just those 3 words, denser matter sinks. Okay? Up here, it's specifically talking about air, but warm, moist air rises. So, because I'm trying to get you to realize that when things are heated, they rise. When things are cooler, they sink. Warm air rises, cool air sinks. Highlight that. Warm air rises, cooler air sinks. It doesn't matter if I'm talking about air or if I'm talking about water. Any fluid obeys this principle. There's even convection currents in the Earth's mantle with that molten rock that is beneath the Earth. It's all hot molten rock, but some of it's hotter, and that hotter rock is a little bit less dense, and it will rise, and a little bit cooler molten rock will sink, and there's a convection current set up within the Earth's mantle. There are convection currents that are set up within the Earth's atmosphere when the air rises and cooler air sinks. There are convection currents that are set up in the ocean. So convection currents and understanding them is really, really important. Okay? All right. The cycling of matter caused by differences in density is called a convection current. In the atmosphere and ocean, convection currents transfer energy as heat from the tropics towards the poles. Okay? All right. Just one more time. Above, right up top here, just put warm fluid rises, cool fluid sinks. Okay, just write it across the top to prove that you're listening. All right, and then I'm going to show you an example of a convection current. All right, when you wrote the notes for lesson 1 and 2, we talked about winds, and one type of local wind are sea breezes and land breezes. And as we get into this unit, you will discover that land, when it absorbs heat energy from the sun, the land gets warmer very easily. Okay? So land heats up quickly, but at night, the land also cools down quickly. Water, it takes a lot of heat energy for water to really change its temperature. So during the day, heat energy absorbed by water doesn't make the water a whole lot warmer. So, you're kind of thinking, well, so what? Well, here's the consequence of what happens. So during the day when the sun is out, land heats up, gets a lot hotter. So the air right above that land gets hotter too, okay? Because it's absorbing some of the heat coming off of the land. And so it warms up, and remember the warmer fluid rises, so the air right above the land starts to rise, okay? Air that's above the ocean doesn't heat up as much, so it's cooler. So what winds up happening is as this warm air rises, the cooler air starts to flow this direction to replace the warm air that's risen. And then it gets heated up and it rises. Okay, so this cycle gets set up. Okay, warm air rising, and when it rises, it eventually cools and it sinks. And then it sets up this whole circulation. So this is a sea breeze, meaning that the wind is coming off the sea, and that happens during the day. Well, you can be at the same location at night, and it's just the opposite. Remember I told you that land heats up quickly, but also cools down quickly. And water, it's really hard for you to change its temperature much at all. So at night, the air above the land is relatively cool, and the air above the water is a lot warmer. So this is where you're having your warm air rise, and your cooler air is now sinking over the land. So the pattern is reversed, and this is called a land breeze. But they're both convection currents. They're both circulations set up because warm air rises and cool air sinks. Okay, so what factors create patterns of global weather? Well, there are both atmospheric patterns and oceanic patterns, or factors from the atmosphere and factors from the ocean. The weather where you live is affected by global weather patterns. Global weather patterns are widespread, covering thousands of square kilometers. They are also often driven by interactions between the atmosphere and the ocean. Okay? Atmospheric factors would include things like our global wind systems, high and low pressure areas, and seasonal changes in wind and pressure. Okay, and this came from the previous readings. Okay, wind systems that flow across the surface of the Earth is an important atmospheric factor. Areas of high and low pressure, seasonal changes, That's basically what we listed here. Okay, important oceanic factors, movement of surface water and sea surface temperature. Okay, so oceanic factors affecting weather patterns, movement of surface water and sea surface temperature. Okay, so like I said, we're laying the foundation to later understand what goes on with weather. So we have to understand first what the atmosphere and the oceans are doing to redistribute the heat that's coming in from the sun. Because remember, the equator gets more than enough heat energy, it gets a surplus, and the poles are at a deficit, and so we have to get the excess from the equator up towards the poles. Okay, on page 454, I'm just going to primarily let you read and highlight what I've already underlined. What are the atmospheric factors of global weather? We've kind of already addressed this. Factor number 1 is global winds. Over here, factor number 2 is pressure belts, and I'll move the screen a little bit. So what I want you to do is just take some time, read through, and highlight what I have highlighted or underlined. Okay? So you may need to pause it. And then factor number 2, pressure belts. Again, pause it and highlight. And then factor number 3, jet streams. Jet streams are narrow bands of fast winds high up in the atmosphere. Okay, so just scroll back and forth, get those things highlighted, and then join me for the next screencast starting on page 457.